Okay, so this is just a kind of brief on what this term is going to be all about. This for third term, we'll be going through some topics. Week one, we have current electricity. Week two, how arrangement of resistors. We also talk about electrical energy and power. Then we move to safety devices, how to detect faults in circuits using simple continuity tester. Also, we will look at the particulate nature of matter, crystal structure of matter. Then we also deal with surface tension and also adhesion, cohesion, and capillarity. We look into that too. Then we move to elastic properties of solids, and that's Hooke's law. Then we look at energy in elastic material, and that will be all for the 10 revision, then examination. So let's look at current electricity. So we have 4 periods that we're using for that particular topic. So at the end of the learning objectives, number one, you must be able to define and explain electric current. You must be able to define and explain potential difference. You must be able to, at the end of the lesson, you must be able to define and explain electromotive force. Also, you have to be able to state and explain Ohm's law. List some materials that do not obey Ohm's law. List and explain factors affecting electrical resistance. Also, you have to be able to explain conductivity as a reciprocal of resistivity. So some of the words that we know that we may not be too familiar with, like charge, potential difference, electromotive force, resistivity, conductivity, will be defined in this lesson. So you have to take notes. So these are the materials that we use. And also, okay, let's go to the main topic. So what's current electricity? In the previous term, we have been able to explain that we have 2 types of electricity. We have the static electricity, which has to do with the type of electricity or the study of electric charges at rest when it does static electricity. But when we look at current electricity, the word current means flowing. So we're looking at the study of electric charges in motion. So let's look at the word electric current. What is electric current? Electric current is defined as the rate of flow of electric charges along a conductor or around a circuit. So the rate, when you hear the rate in physics, we always looking at time, the rate of flow of electric charges. So if you're going to write it mathematically, we have current equals to charge over time. Then you have I. We use I to represent our current. Remember in your year 10 or SS1 first term, current is one of the fundamental unit quantity that we stated. So, and this current is Q over T. That's charge for Q and time for T. So we can invariably say Q equals to IT. If you cross multiply I and T, you have Q equals to IT. The unit of current is the ampere, that's A. So we can have higher values of ampere like milliampere, that's times 10 raised power minus 3, and microampere. We can have that's micro 10 raised power minus 6. Now, what is potential difference? So it then means that when a charge moves in a given time in through a circuit or around this circuit, what we are looking at, the rate at which that charge is moving is the current. So let's quickly look at potential difference, PD, and you can just say PD. So is the PD between any 2 points in a circuit is defined as the work done in moving a unit charge between the 2 points. The potential difference is defined as the work that will be done in taking a unit charge from one point to another point in the circuit. So that's the potential difference. And it has a formula, a mathematical formula, which is work done over charge. So the rate of work done per charge, that's the potential difference. And now you can see potential difference is represented in V, and our work done in W over Q. So the unit is the volts. Let's also look at electromotive force, EMF. The EMF of a cell is the total work done in driving one coulomb of electricity round a closed circuit. Round a closed circuit. When we look at this, the work done that will be done in, or the work in driving one coulomb of electricity or charge around a closed circuit is called EMF. Another way you can say it is the PD between the terminals of a cell when it is not delivering circuit in an external circuit. It's not delivering current, sorry, in an external circuit, or it's in an open circuit. You know, when we have to understand different types of circuits, and from here we have about 3 types of circuit. But before I go on to this, so the potential difference when you measure the terminals of your battery, the potential difference between the terminals of your battery is the EMF you are getting. But when the battery is connected to a load and you measure the potential difference in the circuit, you are no longer getting EMF. It's now the potential difference around about that point. So between the point, excuse me. So that's one thing we have to also understand. It's also measured in volts. Now, for the types of circuit, we have the open circuit. In an open circuit is a type of circuit in which the key is open. That means there is no current flowing in that circuit. And we also have a closed circuit. A closed circuit is that type in which the key is closed. You know, a circuit has some components like the source of energy, which can be the battery or the cell. We also have the key, we have the load, we have the resistor, we have the conductor. So all these are component of a circuit. So when you have an open circuit, it means the key is open. Closed circuit, the key is closed. But in a short circuit, it means that there is no load connected. The circuit is closed and there is no load connected to the battery. So that is short circuit. So let's move on. And this is a very important aspect that you have to also learn. So that's Ohm's law. Ohm's law, that's the law that was derived by or stated by Sir George Ohm, and he states that the potential difference V between any 2 points in a conductor is directly proportional. The potential difference V between any 2 points in a conductor. So when you take a conductor and you look at the potential difference between the 2 points of a conductor, this potential difference is directly proportional to the current I flowing between these points, provided that temperature and other physical constant conditions are constant. So if temperature is constant, pressure is constant, and other physical conditions, then the potential difference will directly be proportional to the current. Now, bringing in a constant of proportionality, we have R, and this R is a constant called the resistance of the conductor. Now, so you can make out the subject formula here and have R equals to V over I, divide both side by I. So there are some materials that do not obey Ohm's law. So we call them non-ohmic conductors. Apart from this one, every other conductor will always obey Ohm's law. So number one, non-ohmic conductor is a transistor. The transistor is a non-ohmic conductor. The diode is also a non-ohmic conductor. The rectifier is also a non-ohmic conductor. Also, we have gases. There are some gases that do conduct electricity, but they are non-ohmic. They do not follow the Ohm's law. Electrolytes, liquid electrolytes, like the copper tetraoxosulfate 6 solution, which is a good electrolyte, conduct electricity, but it is not going to obey the Ohm's law. That means the potential difference is not directly proportional to the current. So that's why we call it the non-ohmic conductors. So transistor, diode, rectifiers, these are all examples of semiconductors. So a simple way of saying it, so you can just say semiconductors are all semiconductors are all non-ohmic conductors. Now let's look at the graph of V against I. We give us a straight line graph, and the slope gives us the resistance of the conductor. You can see that this V against I. When you plot the slope, that's change in V over change in I, and that is our R. So you can see if when the graph I is plotted against V, if we have a graph of I plotted against V, the slope is the reciprocal of the resistance, and that's what we have here. So you can try it out in your experiment. So there are some few factors that affect electrical resistance of a conductor. Number one thing, well, I always give this in form of a code, and that's malt. M-A-L-T. M-A-L-T. I didn't write it here, but you will see material of the conductor. The material with which the conductor is made is a factor. The material as the M, that's what is standing for, the type of material used. Then we also have the cross-sectional area of the conductor, and also we have the length of the conductor and the temperature. So that gives us M-A-L-T. So let's look at the resistance. R of a conductor is directly proportional to the L and inversely proportional to its area. It means that the longer the length, the higher the resistance of the conductor, and the shorter the length, the smaller the resistance of the conductor. But that's a direct proportional relationship. But if you look at the relationship with its area, the bigger the area of the conductor, the smaller the resistance, and the smaller the resistance, the area, the bigger the resistance. So when you combine these two together, it gives you this relationship. This is a joint relationship, and that we bring in a constant of proportionality rule, which is the resistivity of the material used for the conductor. And the unit of rho, if you look at it very well, if you make rho the subject formula here, you have RA over L. So R is in ohms, then A is meter squared over meter. Meter cancel one of the meter squared, so we have ohm meter. In a case where you are using a conductor, cylindrical conductor, we can make use of the area as pi d squared over 4, where your A is the pi r squared, the circular surface of the length. You can use the length. So you can use this formula. Now, resistivity is what we have discussed about that. Resistivity talks about the The ability of the material of the conductor to resist electric current or flow of electric charges in it. So conductivity is the reciprocal of resistivity, and is represented with sigma, which is equals to 1 over rho. Sigma is equals to 1 over rho, and that's what? Per ohm meter, or per ohm per meter. That's the unit of conductivity. So you can say you must be able to, at least by now, you should be able to define electric current, state its unit, define potential difference, define electromotive force, state Ohm's law. You should be able to represent it mathematically, and three materials that do not obey Ohm's law. So let me quickly look at this arrangement of resistor in few minutes. This is just a brief explanation on that. So arrangement of resistors. So you can see in this case we have two ways of arranging resistors. The first way is the series connection. In series connection, the ends are joined together. That is one side joined to the other side of another one, then the next side with another one, and so on and so forth. So we have three resistors, the R1, R2, and R3. So with these three resistors that we have here, in series connection, we observe that the same current passes through the three resistors, but different voltages. So the current is from this source of electricity, the battery that is here, or the cell in this case, because you have just one. So it moves this way and is having the same current in through the O3 coming back, but we have voltage across resistor 1, voltage across resistor 2, V3, voltage across resistor 3. And so when we look at it again, so since the total voltage, let's call the total voltage, which is V here, is equals to V1 plus V2 plus V3. So that's the total voltage. V equals to V1 plus V2 plus V3. So, and we know that V equals to IR. That means V1 will be IR1 plus IR2 plus IR3. Then I is common to the 3, so we bring it out. So you have I into R1 plus R2 plus R3. Then R equals to R1 plus R2 plus R3. So this is the formula for calculating the total resistance in a series connection of resistors. Let's look at the second one, parallel connection. In parallel connection, the resistors are connected side by side or at two common junctions. So you will see that in this. You can see that the R1, the side of this is connected together with this. All are connected at two junctions. This second junction here, the sides, they are placed side by side. The other one is end to end. So you have the junction here, and different currents pass through these three resistors, because at the point of this junction here, we have I1 passing here, I2 passes here, I3 passes through this place. So then the same voltage across the three. So since the voltage is the same, so we have V1 equals to V2 equals to V3 equals to V. So, but the total current is I equals to I1 plus I2 plus I3. And we know from our Ohm's law I equals to V over R. So we have V over R, V over R1 plus V over R2 plus V over R3. If you bring out the V's out, so we have V into 1 over R, V into 1 over R1 plus V into 1 over R2 plus V into R1 over R3. Then these V's can be brought together and they cancel each other. So we then have this formula, which is the formula for the formula for calculating the total resistance in a parallel connection. Yes, there's normal resistance. These are external resistances that are joined to the circuit. But there is a particular thing we call the internal resistance of a cell and lost voltage. Every cell has a form of internal resistance, the opposition to the flow of electric charges in that cell. So this internal resistance is the resistance to the flow of current generated by the electrolyte in the cell as the current passes through the body of the cell to complete the circuit. So that means that there is a particular drawdown in the value of the current based on the fact that there is a particular resistance that the cell itself offers, and that resistance is called the internal resistance. You can see this internal resistance when we multiply it with the current that is flowing in the circuit that is offered by the cell. It's known as the loss voltage across the cell. This is the terminal PD that is measured across this, but across this we are measuring the loss voltage. So from you can see that note that when the cell is sending current through the external resistor, the voltmeter are connected across the cell gives the terminal PD instead of the EMF. So the total EMF is actually the terminal PD plus the lost voltage. You have to note that the total EMF of the cell is the combination, the addition of the terminal PD, which is also always less than the EMF, plus the lost voltage. Lost voltage IR equals, then if you bring this one, take this one to the side, we have E minus V. So arrangement of cells too can be in series and also be in parallel. If your cells are connected in series, the total EMF will be the addition of all the EMFs of the cell. So you have E1 plus E2 plus E3. Total resistance will be R equals to R1 plus R2 plus R3. Then for parallel, if they are connected, if the batteries or cells are connected in parallel, the EMF of the whole thing is, sorry, that's a NEPA just took the light. There is a break in transmission. So okay, so we look at this again. So let's look at it. Let me use this my, so you can see I'll end so very soon now. So this is the EMF, total EMF E1 equals to E2 equals to E3, but the current is very strong. So we'll deal with the examples later. These are examples we have to deal with later. So have a wonderful day And if you have any question, kindly drop your question on the comment section. Please subscribe and like this channel. You can also share our videos with your mates, your classmates, or your colleagues. If there is any problem, we can always help you to solve them. Okay, this brings me to the end of this uh, introduction class to for the current electricity. In the next class, we'll be looking at the calculations, how to calculate the total sum of resistances, EMF, and the likes. Okay, goodbye. Till next time when we meet. I remain uh, Prof. Dan, the administrator of L. George Academy. Bye.